All right. Okay. Hello, everyone. I've been getting a lot of questions, about a lot of emails about the question section for the Lab 4 report, and I'm making this video here. Hopefully, it will help you guys out. I will say before I start that despite what a lot of people seem to think, every one of these questions, except for questions 6 and 7, do not involve any calculations on your part. They are purely conceptual questions. Also, they are one-sentence response questions. Okay, so I mean that might surprise you, but that is indeed the case. And I was hoping that if you had gone through the lab manual or at least watched the videos I put up, that you would be able to answer these questions. But seeing as that some people have not been able to still, then I'm hopefully making this video, and hopefully this will be all you need to answer all these questions. Okay, so I'm gonna go through them real quick. Unfortunately, because I'm currently using Xbox Bar, I cannot switch screens, but I'm gonna write everything over here and erase it as I go along. Okay, but anyways, so let's start. So we have here question 1. Okay, let me add notes here. All right, question 1. All right, so it said that if you have three-phase power being fed into an induction motor, then the net instantaneous power, okay, because remember, three-phase power, you have three phases. Each one of those is a sinusoid, but if you add those sinusoids together, the net instantaneous power is going to be constant, okay, despite each of the phases being, oscillatory. Why might that instantaneous power being constant be a good thing? All right, and I was saying, I'm thinking mechanically speaking here, okay. Well, if you just thinking about it, that electrical power going in, okay, is going to be what is converted to mechanical power. All right. So if your electrical power going in is constant, that means the mechanical power going out is also going to be constant. And we know that power out in the motor's case is torque load times its speed. Okay. So if this is constant and your load is not changing, then it's going to be constant speed. It's going to have constant speed. Or you don't even need to go that far. You can just say that the output power, that output mechanical power is going to be constant, which means you'll have a motor that is stable. It's not going up and down. All right. If instead you had single phase power being delivered to the motor, then you will find that it will oscillate. The speed at which it's turning at is going to oscillate, and that's not something you want to do. All right. So that's why that three-phase power is very helpful when driving a motor. Okay, and that's it for that question. I'm just going to erase this away. All right. Here's the second question. What kind of AC machine is this? Some people have sent me lab reports, and they said this is an induction machine. Okay. I just want to say that's obviously the case. So that's not what I was asking. I was as in particular asking you, what kind of induction machine is this? Okay. This is definitely not going to be a synchronous machine, because I'm assuming that you guys haven't learned that yet. So the only machine you've seen so far is an induction motor. Okay, so I mean, this is going to be an induction motor. But I mean, there are ways that you can specifically say this is an induction induction motor, but like I wasn't expecting you to go that far. You didn't need to think about all different kinds of machines. You've only been shown induction machines, so this is definitely an induction motor. The other thing, the other dead giveaways in the lab, and what you guys have seen in the relevant theory information section, that was the cage rotor induction motor of the lab. But I also said that there was also a wound rotor induction motor. Okay, and that's it. This is the wound rotor induction motor. So you could have, gotten the answer by thinking in that manner. However, there's a few other dead giveaways. Okay, so first of all, if you conclude that this is an induction machine, okay, and there is a way to do that. I'll explain that in a second. But if you conclude that this is an induction machine, then induction machines have only two kinds of rotors. Either it's a cage rotor or it's a wound rotor. And I don't know about you, but these over here look like copper. That there looks like copper to me, which means windings, which means the rotor has windings. And so this is clearly a wound rotor. And so this overall is a wound rotor induction motor. And that's pretty much it. That's the dead giveaway. All right. The other thing that you could also see is that I said wound rotor induction motors also have the property where you can access the rotor circuit. You can access this winding through these brush slip ring combinations over here. And that allows you to put in extra resistance into your rotor circuit, which allows you to vary the torque speed characteristic curve. Okay. So if you have access to the rotor circuit like that, that's what that'll give you. Then if this is an induction motor, again, that is purely a property of wound rotor induction motors. Okay, cage rotors, you don't have this. You don't have this setup over there. You don't have this configuration. So that's another way that you could have gone about concluding that this is a wound rotor induction motor. The final thing I'll say is, if you did not know that this was an induction motor, then I can tell you that the only machine that has 3 brushes like that, which means 3 slip rings, is a wound rotor induction motor. Okay, there are also synchronous machines that have slip ring combinations like this. Okay, but you'll find that they will only have 2. All right, and that's to feed the rotor to provide DC current. Okay, that field current. But anyways, the wound rotor induction motor is the only one that has 3 slip rings and 3 brushes, and that's the other thing I wanted to point out. So by any of those 3 logical pathways that you could have gone, clearly this is a wound rotor induction motor. Okay. Number 3, if a motor is pushing some load and stalls, it starts to heat up. Why? All right, so what did we say? For an induction motor, if it's stalled, first thing that you'll note is that its slip ratio S equals 1. If its slip ratio is 1, that means that the rotor's circuit, its resistance, is going to be at its lowest. Okay, the impedance of the rotor circuit is going to be at its lowest, and that's something that you can observe if you just draw up the equivalent circuit diagram. I'm going to draw it over this question over here. Okay, I'm just going to do that real quick. All right. Okay, this part over here of your equivalent circuit, that's the rotor part. Okay, and this value over here was R2 over S, and so this S over here is 1. In the other case, in the other extreme, it's 0, but in any case, it's pretty much 1. If it's 1, that means this is going to be as low as it's going to be, which means the overall impedance is as high as it's low as it's going to be. So any voltage applied will cause high currents in the rotor. And if you have high currents in the rotor heats up. Okay, so that's pretty much the answer to that question. Okay, so I'm going to erase that. Okay, number 4, if I operated my induction motor at half synchronous speed, is its efficiency better, worse, or the same as it would at near full synchronous speed? And why? Okay, this is something, this and actually pretty much every question after this, by the way, is directly from the videos I put up. Okay, and in those videos I said that, first of all, recall the equation, P converted equals to 1 minus S P gap, P air gap. Okay, so as power is coming into the stator of your induction motor, how much of that power gets wirelessly transferred over the from the stator to the rotor? That's P air gap. And then how much of that power gets converted to mechanical power? That's what P converted stands for. Has a relationship that it is 1 minus S times the P air gap. So from this, I concluded, okay, in the video, that motors with high S, with a high value of S, have less efficiency. Okay, which means that motors that are rotating at a slower speed than if their operating condition is at a slower speed than synchronous speed, okay, that their efficiency is lower. So that answers this question. Okay, so if your motor is at half of its, if the slip ratio is 0.5, then it's operating at speed that is half of synchronous speed, which means it's going to be less efficient than if it were operating at synchronous speed. Okay, and also just from that equation I wrote down, you can see that you can answer this question, which says that if the power transferred over the air gap, so that P air gap was 1 kilowatt and your slip ratio was 0.5, then how much power is being converted to mechanical power? Well, I mean, clearly it's just 0.5 times 1 kilowatt. Okay, so you can answer that for yourself. Say I have 2 induction motors. Both have the same pull-out torque, but motor A has a higher start torque than motor B. Which one is more efficient at operating conditions? Okay, so we have 2 motors over here. Let me draw this out real quick. Okay, let me draw this curve here. This is my speed. This is my torque. Okay, and it says over here they have the same pull-out torque. So I'm gonna designate that by a line. I'm just gonna say that's T pull out. Okay, that's the torque pull out. And it says that they have the same one, but motor A has a higher start torque than motor B. If you watch that video I put up, you'll find that the motor with the higher start torque, first of all, let's just draw any one of them. Let's say the motor A has a curve that looks like this. Okay, that's how it's going to look like. Motor B has a higher start torque, but the same pull-out torque. So it starts off higher. Okay, it starts off higher, but it has the same pull-out torque, which means its curve is going to look like this. Okay, and that's again directly from the video. So if first of all, that's what you visualize in your head as soon as I mentioned that first sentence. Okay, which one is more efficient at operating conditions? Well, what's operating conditions? Operating conditions, like I say in the video, is a little after the peak. Okay, this is the peak. A little after it is going to be where the motor operates. So for this red motor, it's going to operate there. For this blue one, it's going to operate here. Clearly, this one has a smaller slip ratio than this, which means that the blue motor has a higher efficiency than the red one. Okay, and that comes again from the video, and that should be in line with the logic used for the previous questions. Okay, so let me erase that. Unfortunately, there's no undo button, so this is a little bit more annoying, but yeah, so that's it from that. Question number 6, this is directly from the part A procedure. You just follow that and you do the, conclude what the equivalent circuit will be for the wound rotor induction motor, and your answers to number 6 are what take you through the next 3 questions. Okay, so you need to do this part properly, but this is the least you can do for this lab is follow the procedure I did in part A. Okay, and that's what this question is asking you to do. This is the only one along with number 7 that as you do actual calculations. Okay, what's number 7? Based on your calculated parameter values, what do you predict the wound motor's pull-out torque will be? Well, if you did this right, okay, if you did this the calculations right, let me go over real quick to what I have for part A. Okay, the results I have for part A. Okay, my equivalent circuit was this. All right. What you're gonna find if you did this right is that all of these are the same pretty much, except the series values over here. I'm not going to tell you what exactly, but they're going to be a little higher. Okay, and this one also is going to be a little higher. This secondary, the rotor's resistance. Okay, and if you go back to the section over here of the lab manual, okay, you'll find that you'll have this equation here, torque induced max. This is what the pull-out torque is going to be, and observe that it has a direct relationship between what this RTH, X2, XM, all those values are. And if you go to RTH, you'll see that X1, that's the series resistance, okay? And RTH, RTH is that. It has the series resistance over there, a series reactance, sorry, over there. You're going to see that the wound rotor's induction motor has a smaller series resistance. I'm sorry, I think I said it had a higher one. It has a smaller one. If it has a smaller one, RTH, oh, I mixed this up. Sorry, I mixed it up for a second. X1 will be higher, which means that RTH will be smaller. If RTH is smaller, you can see if all these values are smaller, that means overall this quantity is going to be higher, so it will have a higher start torque. Okay, so that's one way you could have answered this question. The other way is you could have plugged in the values directly into this equation, and you would have gotten your answer. Okay, so you literally use this equation and you would have gotten your answer. Okay, so that's that question. Question number 8. Compare the values you computed. Okay, for the compare those to the cage rotor one. Okay, based on just the parameter values alone, which one do you think has the higher start torque, and which one do you think is more efficient at operating conditions? Well, I mean, like I said, if you look at the equivalent circuit, you'll find that its R2 value for the wound rotor induction motor is going to be higher. If you have a higher R2 value, that means that your curve will be shifted to the left a little bit, which means you have a higher start torque. Okay, so the wound rotor induction motor will have a higher start torque because it has a higher R2 value. Okay, and again, the logic for that, the reasoning, everything is in the videos. Okay, and also in the lab manual if you read through it. All right, and then also you'll see that the series resistance values are higher, which means that the pull-out torque, the max torque, is going to be higher. Okay, or sorry, yeah, well, that was the answer to the previous question. It's just yeah, which one has a higher start torque? Well, again, like I said, that's obvious. That's what I just said. So because the wound rotor's R2 value is higher, it has a higher start torque, which means that at operating conditions, again, that was the other part of the question. At operating conditions, it's going to have a larger slip ratio, which means it's going to be less efficient. Okay, and again, that goes in line with the logic used from the previous questions. Finally, question 9. So far for question 7 and 8, I kind of have you just guess based on looking at the parameter values. For question 9, I go ahead and plot for you what the actual torque speed curve for both of them are. I plot them on the same plot, and then you can kind of see, and I ask you, based on looking at these plots, does that change your answers to the previous two questions? And I mean, clearly you can see that, if you'd followed the reasoning right, then you should have been right, correct. But you can see that clearly higher start torque, okay, for the orange curve is the wound rotor, the blue curve is the cage rotor. Clearly the wound one has a higher start torque, and again, its operating condition is going to be somewhere there, and for the cage rotor, it's going to be somewhere there. This one has so clearly this is a higher slip ratio than this, which means that the orange curve, which represents the wound rotor induction motor, is going to have is going to be less efficient at operating conditions. Okay, so that's the first part of that. And then I ask you, based on looking at these curves, what kind of application would make sense for the one with the higher start torque? Okay, and I say ignore these actual values, the exact torque values. I'm just saying look at the curve and say what do you think makes sense for an application like this? Well, what did we say about this curve? We said it has a high start torque and it has high slip ratio, so it's inefficient at operating conditions. Okay, so literally you just go off of that and say if the motor has, if you have an application where you're lifting a heavy load, so that means that there needs to be a high starting torque, that's where you'd use the wound induction motor. Okay, and if it doesn't need to spin very fast, especially when compared to 60 hertz frequency, then that's what your operating condition is going to be, and so it's totally fine. So so that's the kind of motor, that's the kind of application that this motor would be for. Whereas, for example, the cage rotor motor, if you'll see its operating conditions there, it has a smaller start torque. If you have a consumer device, okay, those devices typically do want to be spun at a little bit of a faster rate. And the start torque is not super duper important, but efficiency is important. So consumer devices typically have this kind of curve that you see for the cage rotor motor, whereas industrial applications, they have the other curve. Okay, and in fact, you can get there is a little more, and you can get more involved into it, but I wasn't expecting any more than that, really. But yeah, you can get more involved. You can get all sorts of different torque speed curves for various different applications, and in fact, there's a whole set of standards for that. But anyways, that's pretty much it. So, um, that's the last question. So as you can see, I was talking through this because I was trying to explain, but in your head, this should have been fairly straightforward and quick to do if you had understood the lab manual and had understood the videos. Okay, but like I said, I made this video in case you had some trouble with that, and people did indeed have trouble with this, and I hope that helped. I really do hope that helped. And I should also point out that I'm asking these questions not to be extra or anything, but these questions relate to the most important thing that you need to take away from this chapter on induction motors, and that's concerning their torque speed curves. If you're going to have an application that uses motors, your main concern is going to be the torque speed curve. And these questions are basically asking you about your intuition on torque speed curves for induction motors. Okay, so anyways, that's that. All the best. Okay.